Yes. Now let us see the electrophoresis property of colloids. What is electrophoresis? See, if you apply an electric field, introduce an electric field into the given sol, the sol particles will start to migrate either toward cathode or toward anode. See, under the applied electric field, the sol particles will move toward cathode or anode, any one direction. This movement of sol particles either towards cathode or anode under the applied electric potential or electric field is known as electrophoresis. Electrophoresis experiment or electrophoresis property of sol indicates in given sol, all sol particles carry either negative charge or positive charge. That means any one type of charge. Sol particles, all sol particles present in the given sol may carry positive charge or negative charge. Because of presence of only one type of charged particles, dispersed particles in the given sol, sol is highly stable. Because of presence of same charge, the sol particles move away from each other in the system. As the result, aggregation, association or coagulation does not occur in the system. That is responsible for stability of sol. You can determine the actual charge carried by the sol particles of given sol by performing one simple experiment. That is, you just consider an instrument of this type consisting of an U tube. Okay. It is connected to a dropping funnel or funnel provided with a stopper with the help of a rubber tube. Here in the sol, in this dropping funnel, sol is taken. Sol whose particles charge to be determined. Now carefully introduce this sol into these two limbs of the U tube. That is like this. Okay. So given sol is present in the two limbs of the U tube. Now carefully place little amount of distilled water, that is pure water, above the surface of sol in the two limbs. What is this? Distilled water. Okay. In the distilled water, place two platinum plates. Just dip platinum plates, or you can say platinum electrodes. Then connect these two plates or electrodes to a current source and pass the current. On passing the current through the sol particles will begin to move either toward anode or toward cathode. You can see the movement. On passing the current, the level of sol in any one of the limb falls, or in any one of the limb increases. See, if the sol migrates from anode to cathode, the sol level in the anode compartment decreases, whereas cathode compartment increases. This indicates the sol particles are moving from anode to cathode or similarly cathode to anode. This gives the actual charge present on the salt particles. So, this in fact confirms in the given salt, all salt particles carry either positive charge or negative charge. It means only one kind of charged particles present in the given salt, and it is responsible for its stability. Okay. This is about electrophoresis. I repeat, electrophoresis. Electrophoresis is the movement of salt particles either towards cathode or anode under the applied potential difference or electric field. See, if salt particles migrate towards cathode, then that movement is known as cataphoresis. Cataphoresis is the movement of salt particles toward cathode under the applied electric field. Similarly, if the salt particles migrate toward anode, then it is known as anophoresis. Sometimes electrophoresis, also known as anophoresis or cataphoresis. These two terms indicates the actual movement or direction of movement of salt particles under the applied potential difference. Next point is another interesting thing here. If you place an obstruction to the movement of salt particles during electrophoresis, if you apply an obstruction, that is placing some blocks in the U-tube which checks the movement of salt particles under the applied electric field. See, if you apply an obstruction to the movement of salt particles during electrophoresis, the movement of salt particles stops, but medium particles will begin to move. Salt particles movement stop, but medium particles will start to move. This is known as electroosmosis. Short note nalli keluvanthaddu. What is electroosmosis? Or I write a note on electroosmosis antare. See, during electrophoresis experiment, if obstruction is placed to the movement of salt particles, the movement of salt particle is stopped, but the movement of medium particles, that is dispersion phase, medium, will begin. This is known as electroosmosis. Okay. Next bit is, the question is how the salt particles get their charge. That means there are two types of salts based on charge carried by the salt particles: positively charged salts and negatively charged salts. Positively charged salts are those salts in which salt particles carry positive charge. Negatively charged salts are those in which salt particles are carrying negative charge. Question is how the salt particles acquire electric charge, gain the charge. It is believed that the charge on the salt particles is mainly due to preferential absorption of some ions on the salt particles. That is one reason. Another reason is, or thing is, during the preparation, the salt particles may capture electrons. It is believed that during the preparation of metal salts by Bredig salt method, the salt particles may capture electrons and gain the charge. But the important one, most accepted reason is, during the formation of salts, the salt particles actually lead to a preferential adsorption. Salt particles prefer to absorb some particular ions, only some particular ions, charged ions on their surface. So, charge on the salt particles is mainly due to preferential adsorption of some ions present in the system. I will give an example here. See, the metal salts prepared by Briggs arc method always carry negative charge. Metal salts are examples for negatively charged salts. How negative charge comes on the salt particles? It is important. During the preparation of metal salts by Briggs arc method, very often we use one important thing, that is KOH, little amount of KOH, potassium hydroxide or sodium hydroxide. This KOH or NaOH in solution gives potassium ion and hydroxyl ions. Okay. These hydroxyl ions are adsorbed on the salt particles, preferential adsorption. Preferential adsorption. These hydroxyl ions adsorbed on the salt particles, hence metal salts carry negative charge. The negative charge on metal salts prepared by Briggs arc method is due to the preferential adsorption of hydroxyl ions on the salt particles. Similarly, arsenic sulfide salt. Arsenic sulfide salt. It is actually prepared by passing H2S gas through a solution of arsenic oxide. When you pass H2S gas through solution of arsenic oxide, arsenic sulfide salt is formed. This arsenic sulfide salt is negatively charged one. It carries negative charge. Anionic type salt it is. This negative charge on arsenic sulfide salt is due to a preferential adsorption of sulfide ions on the salt particles. See, this H2S gas, it is a weak electrolyte. In solution, it dissociates to give hydrogen ion and sulfide ion. In the solution or in the system, these ions are also present along with these components. Now, this arsenic sulfide salt particles prefer to adsorb these sulfide ions on the surface of them. Hence, arsenic sulfide salt is negatively charged. See, hydrated ferric oxide. Hydrated ferric oxide. Well, you can say ferric hydroxide salt. Hydrated ferric oxide, it is Fe2O3 XH2O. Okay. Hydrated ferric oxide. This salt is positively charged one. It is positively charged. It is formed by adding ferric chloride solution into boiling water. When ferric chloride solution is added into boiling water, ferric hydroxide salt is formed first. FeOH thrice salt is formed. It converts into hydrated ferric oxide salt. Okay. This salt carries positive charge. It is an example for positively charged salt. Normally, hydrated metal oxide salts are positively charged salts. The positive charge on hydrated ferric oxide salt is mainly due to the preferential adsorption of ferric ion on the salt particles. See, ferric chloride in solution dissociates to give ferric ion and chloride ions. Some of the ferric ions get absorbed on the salt particles. Ferric ion carries positive charge, hence hydrated ferric oxide carries positive charge. Excuse me. Next one is another interesting thing is there. So, charge on salt particles in the given salt is mainly due to the preferential absorption of some ions. See, when you add silver nitrate or when you mix silver nitrate and potassium iodide solution, equimolar, when you mix equimolar amount of potassium iodide and silver nitrate solutions. See, first silver iodide, in fact it is precipitate. Silver iodide precipitate is formed along with potassium nitrate. What is this? Precipitate. If you write arrow mark in the downward direction, indicates it is precipitate. On the other hand, if you add a little excess of potassium iodide, into silver nitrate solution, first silver iodide precipitate is formed, okay, in presence of excess amount of potassium iodide, it breaks to form silver iodide salt, that is due to peptization. Okay. So, when you add a little excess of potassium iodide into silver nitrate solution, silver iodide salt is formed. It is found that this silver iodide salt carries negative charge. It is the negatively charged salt because in the solution there is excess of potassium iodide. This potassium iodide dissociates to give potassium ion and iodide ions. These iodide ions get absorbed on the salt particles of silver iodide salt. As the result, the silver iodide salt gets negative charge. Generally, it is written as AgI I minus. AgI I minus. AgI silver iodide salt on which iodide ions are absorbed and net charge on the salt is negative. Now, if you add a little excess of silver nitrate, or if you consider a little excess of silver nitrate solution, then the reaction is same thing. That means silver nitrate reacts with potassium iodide to form silver iodide precipitate. Then excess of silver nitrate, it is precipitate. In presence of excess of silver nitrate, here in this case potassium iodide is acting as peptizing agent or peptizer. Here silver nitrate, it is also acting as peptizing agent. This silver nitrate electrolyte breaks this precipitate of silver iodide to form silver iodide salt. Okay, that means silver iodide salt is formed through peptization, in which silver nitrate is acting as peptizing agent. then this silver nitrate excess present in the solution dissociates to give silver ions and nitrate ions. Okay. Now these silver ions get adsorbed on the silver iodide salt particles. As the result, the silver iodide salt gets positive charge. Now it becomes positively charged salt. That means here you can write it as silver iodide Ag plus. Okay. Here the salt is carrying positive charge. Here the salt is carrying negative charge. Negative charge, both are same salts, silver iodide salts. In one case, negative charge is present on the salt particles. In another case, positive charge is present on the salt particles. This is due to preferential adsorption. Here, silver iodide salt particles prefer to absorb iodide ions on them, whereas same silver iodide salt prefers to absorb silver ions on them. Okay, this is one point. So in the given salt particles carry either positive charge or negative charge, any one type of charge. You just consider this is the salt, given salt, on which positively charged particles are adsorbed through preferential adsorption. As the result, on the surface of salt particles, positively charged ions are adsorbed. That means these positively charged ions or charge is fixed on the salt particles, and this layer is known as fixed layer. It is known as fixed layer. Now, this layer tends to attract the counter ion present in the solution or system. System nal counter ion idde irutte. Now, this charge tends to attract the counter ions present in the solution. As the result, the oppositely charged ions, the negatively charged ions present in the solution come close to this fixed layer, and there is another layer of charge is formed at the surface. This layer is tending towards the medium, and it is said to be diffused layer. Diffused layer. So on the salt particles, there exists an electrical double layer of opposite charges. See, salt particles there. On the salt particles, preferential adsorption of one type of ions are adsorbed, and those ions are weakly linked with the counter ions of the solution, counter ions present in the solution. So there exists an electrical double layer on the surface of salt particles. Due to the existence or formation of an electrical double layer of opposite charge, keep it in mind, electrical double layer of opposite charges on the surface of salt particles, a sort of potential is developed here. That potential is known as electrokinetic potential or zeta potential. Zeta potential. What is zeta potential? It is the potential developed at the interface of salt particles in the given salt, where an electrical double layer of opposite charges exist. Okay, this is known as zeta potential or electrokinetic potential, and of course it is about charge on the salt. The next bit is Coagulation, another important property of salts. Coagulation. Okay. You know, in the given salt, all salt particles carry either positive charge or negative charge. Okay. In given metallic salt, metal salt particles carry negative charge. In the arsenic sulfide salt, all salt particles carry negative charge. Okay. In case of hydrated ferric oxide salt, all salt particles carry positive charge. Now consider a salt carrying positively charged salt particles. That is, it is a positive salt. Okay. When you add an electrolyte, any electrolyte, you know, electrolytes are the species or substances made up of oppositely charged ions. They in solution undergo dissociation into constituent ions carrying positive, either positive charge or negative charge. That is sodium chloride. Sodium chloride in solution dissociates to give sodium ion, chloride ion, like that. When you add an electrolyte into a given salt, whether it is positive salt or negative salt, the charge present on the salt particle get neutralized by the opposite charge ions, or by the ions carrying opposite charge. Here, in the case of positively charged salt, the positive charge of salt particles are neutralized by the negatively charged ions. See, because of presence of same charge on all salt particles repel each other. They tend to move away from each other. Okay. When you add an electrolyte into the salt, the charge on salt particles get neutralized, removed. When charge on the salt particles removed, the salt particles will tend to coalesce, tend to associate, aggregate. As the result, their size increases, then gradually tend to settle down. That process is known as precipitation. Generally, it is known as coagulation. So, what is coagulation? Coagulation is the process of neutralization of charge on the salt particles by the addition of an electrolyte, or the process of precipitation or settling down of salt particles by removing of charge present on them by adding an electrolyte, suitable or electrolyte, is known as coagulation. It is one important thing. See, if you add an electrolyte into a negatively charged salt particle, negatively charged salt, the positive charged species of added electrolyte neutralize the charge of salt particles and cause the coagulation. On the other hand, when you add an electrolyte into negatively charged salt, positively charged species or ions of added electrolyte neutralize the charge on the salt particles and cause the coagulation. So, coagulation is mainly due to neutralization of charge on the salt particles. This is regarding coagulation. See, the coagulating power of ions, that is, the efficiency of an ion to cause the coagulation of given salt depends upon its valency, that is, the charge present on that ion. This statement is known as Hardy-Skulls rule. Hardy-Skulls rule. Hardy-Skulls rule states the efficiency of an ion causing coagulation depends upon the charge carried by it. Higher the charge on the ion causing coagulation, higher will be its coagulating power or strength. You just see, you just consider a negatively charged salt and you have to coagulate this negatively charged salt. You are given 3 electrolytes. Say, of course, to coagulate or to neutralize the charge present on the salt particles of this salt, we need positively charged ions. Okay? So, positive charge ions are required to neutralize the charge present on the given negative salt. You are given sodium chloride, barium chloride and aluminum chloride solution. Among these 3, which one is most effective coagulating agent? Most effective to cause the coagulation of given amount of this negatively charged salt? It is the question. See, the sodium chloride in solution gives sodium ions, barium chloride in solution gives barium ions, aluminum chloride in solution gives aluminum ion. Sodium ion carries only one positive charge, whereas barium 2, aluminum 3. Higher the charge on the ion causing coagulation, higher will be its coagulating power. Higher will be its coagulating power. So, to bring the coagulation of a negatively charged salt, among these 3 electrolytes, aluminum chloride is most effective because aluminum chloride gives aluminum ion which carries highest charge among these 3. So, least effective is sodium chloride. Similarly, in the case of coagulation of a positively charged salt, among these 3 electrolytes, say sodium chloride, then sodium sulfate, then aluminum phosphate, which is most effective coagulating agent. It is the interesting thing. See, to cause the coagulation of positively charged salt, we require negatively charged ions. The negatively charged ions which carry more negative charges will be more effective coagulating agent. Here, the sodium chloride on dissociation gives sodium ion and chloride ion. Sodium sulfate on dissociation gives sodium ion and sulfate ions. Aluminum phosphate on dissociation gives aluminum ion and phosphate ion. Carefully see the charges present on the negatively charged ions. These negatively charged ions, chloride ion is uninegatively charged ion. Sulfate bi-negative. Here tri-negative. Phosphate ions carry more negative charges than sulfate ions, which in turn more than chloride ion. So to cause the coagulation of this positively charged salt, among these three, the most effective coagulating agent is aluminum phosphate, because phosphate is trivalent ion or carrying 3 negative charges. This is about Hardy-Scull's rule. I would like to stop it here and continue in the next class.